Welcome once again to the Set-Theory Seminar. Our speaker today is Philip Welch from the University of Bristol. And one of the great things about virtual seminars, even though there are many disadvantages to the whole Zoom thing, is getting speakers like Philip in New York. So I'm very happy to hear from you today, Philip. And Philip is going to speak about the universe constructed from a set or class of regular cardinals. All right, Philip, take it away.
Fine, thank you. Thank you for the intro, Vika. No, I'm very pleased to talk to this seminar. In fact, I think it's much safer in some sense talking to the CUNY Grad Center by Zoom than actually in person. I mean, the last time I gave a talk in person at the CUNY Grad Center, I ended up in the NYU hospital around the corner because it's a very hazardous, dangerous place, the CUNY Grad Center seminar.
Yes, I remember this. That's right. Yeah. There's so many reasons to do this over Zoom.
For sharp projections from the whiteboard screen and so on that laid me low. And, in any case, so I'm now sitting very comfortably here in Bristol and well at home, as you can see behind me. What I'd like to do is to talk about, well, some continuing work. I mean, a couple of years ago, I was giving talks on L card, which was basically L constructed from a predicate for the cardinals. And I'm going to start today's talk by reviewing that. In fact, going through a fair number of details of that again, for those who perhaps are not familiar with it. But then the extension of that is to look at a predicate for just the regular cardinals. Right? So this will give us a model which is a constructible closure L of reg, if you like. And part of this work was, well, originally was motivated by a paper or preprint of Juliet Kennedy, Menachem Magador, and Yoko Fananen, where they were looking at how to construct universes which were L-like, but not using just first-order logic. So they would construct a universe using some subsystem of second-order logic. And these logics were often involved using quantifiers, which had occurred in the literature, but which were non-standard. For example, an equicofinality quantifier or an equicardinality quantifier or a stationary quantifier, Magador-Malletz quantifiers, and so on. Right? So you can view this as part of that program, or you can just forget about that altogether. And indeed, I shall only talk about that a little bit at the end, if there's time. Just view this as just asking questions about L of various predicates. So let's start by doing that. I will share the screen, and of course you should, you're quite welcome to interrupt me at any point and ask questions here. So let me try opening this up. Right, I hope that looks fine. So tell me if it's not. So as I said, the background here is some older material looking at L of P, where I've got a CUB class, P contained in the ordinals. And this kind of corresponds to what I was saying is the Hertig quantifier model. And of course, the cardinals, can you see my mouse there? It's underneath card. Does the mouse come over? No.
In fact, we don't see anything other than the title of your talk and the blue rectangle.
Oh, really? Right. So something is not working. So you should be able to see the first or second slide. No. Okay.
No, it's still all we're seeing was the title slide.
Right. Okay.
Before it was working.
Yes, but maybe maybe I hadn't tested it fully.
No, but before I could see the second slide.
So I'm going to,
Yes, we did see the second slide before the recording started.
So I don't know why it's not working now.
Maybe we can just all remember what the second slide said and pretend it's there.
That stuff, I don't focus on it.
so I'm just making sure I probably opened the wrong window or started sharing the wrong window. So I'm just making sure by getting rid of the other windows. Right. So here should be Eve Klein again. And this should be the second slide.
Perfect. Yes.
Yes.
Yeah.
Can
Yeah.
you see my mouse?
Yeah.
Yes,
Yeah.
we see the pointer.
So the second part of the talk is going from this. So P here could be the class of cardinals. These are, after all, a closed unbounded class. So this is what people might want to focus on if you are interested in this Hertig quantifier model. We want to go from, do something new. So we go from L card to L reg. So reg will be the class of regular cardinals, or indeed, as in the title of my talk, for any subset or subclass of the regulars. Much of this will apply to. And the corresponding model here would be C of R in the Kennedy, Magadorf, and Arnhem notation. So part one, we consider CUB classes of ordinals and the universes we construct from them. Now, of course, if V equals L, things are terribly uninteresting. All we're going to get is L all the time. It's also the case, I view kind of forcing constructions over L as also being not terribly interesting. We can get various kinds of classes and get differing models if we force over L. But what is more interesting is when we assume there are some large cardinals in the universe. And in particular, not very large cardinals, actually, very modest large cardinals. And what we'll see is that we'll get a kind of uniformity appearing. So here are just some typical examples of classes P, right? One could take the closed unbounded classes of those alphas where V alpha is sigma in elementary in V. One could take the class of all the uniform silver indiscernibles. So we're assuming that all reals have sharps. So we could take all of the classes, all classes of silver indiscernibles for reals and here, and take their intersection. So again, this is a closed unbounded class of uniform indiscernibles, or L card itself. Of course, a priori, when you first look at this, there's perhaps no reason to think that one has any kind of uniformity. What can we say about these models? Do they have anything in common at all? And perhaps there's no a priori reason why, for example, the GCH might hold. You could, who knows what kind of information one can code into this closed unbounded class P. And these classes are so different, one would not perhaps immediately think that these models are pretty similar, actually. So one can ask, are they models of GCH? What are their descriptive set theoretic properties of their reals, and so forth? So what we can show actually is that assuming modest large cardinals, right, that the models themselves actually all have the same reals, right? And in fact, more than that, right, they turn out to be elementary equivalent. Right? So actually, they kind of have the same theory, right? So the C17, these are the alphas where V alpha is a sigma 17 substructure of the universe. And actually, that's got the same theory as just L of all the cardinals. And the same here for the uniform indiscernibles. I think if you're slightly surprised by that at the beginning, then that's good. You can keep that sense of wonder and surprise with you. I mean, certainly, if this is true, you could see certain kind of things going to have to hold. I mean, the true omega 1 of V, which is a cardinal, of course, is rather different from the first alpha that's here. So it's going to have to be the first omega 1 of, the true omega 1 of V is not going to be definable in here. In fact, omega 1 of V is itself going to be a large cardinal inside this model. Right? So if this is going to hold, it's certainly going to be the case that the cardinals of V are not, although this predicate gives us the information as to which ones they are, L of card doesn't kind of give you the properties of cardinals that we can see in V. And so the reason behind this is that actually all of these models we can view as some kind of class prickly generic extension of their core models. Right? And they've all got the same core model. So to specify that a little bit more, right, let's think about what we've got. So what we're going to do is define this mouse-like thing. So this little OK is, you should think of it, this is like O sharp. So as O sharp is to L, so is OK to some other definable inner model, right? The K is for cookery, but I won't spend time talking about that now. So what you think of this as it's a iterable structure. It's a countable iterable structure, and it generates a model. And what it does is, as you iterate the top measure of this countable iterable structure, you get a proper class of ordinals, which is like indiscernibles for L. It's CUB beneath each uncountable cardinal. So that if you then took any CUB definable subclasses of this C, we get the result I was indicating on the previous page. The reals are the same and the models are elementary equivalent. So it's kind of a slogan here, which is we're trying to see if large cardinals affect somehow the informational content of L card or some of these other models. And the idea is, the maxim here is that once we get to a certain point, they do not. We can do forcing constructions over L and get various kinds of results, or even over L of O sharp or O triple sharp, or over L mu. But once you get to this mouse OK, these models in one sense are the same. Right? So what does OK look like? So again, this is supposed to be a little bit reminiscent, if you've seen these things before, of what O sharp or mice might look like. There's a level of the J hierarchy here built on a kind of filter sequence. We're below extenders here, so we're not even talking about measures of order 1. Right? So we're just talking in the realm of measurable cardinals here for this whole talk. So there's a filter sequence in the structure, and it's got this top measure. And the point is that this is the first kind of mouse, or first iterable structure, if you like, which has a measure with unboundedly many measurables below it. So it's really quite simple, small mouse here. And when we iterate this top measure, we leave behind a closed unbounded class. So we can take iterated ultrapairs of this M0 using this top measure and its images, and we'll get these intermediate models as we keep iterating them up. M iota for the iotith iteration of M0 by this top measure. So they generate or leave behind this model, which I'll call L of E0. And we just look at the sets that are left behind that are of hereditary cardinality less than kappa I in the ith model Mi. And this turns out to be the same as this here. So the critical points, right, here of this mouse as it iterates, and we'll call them kappa iota here, these are indiscernibles for the model that's been left behind. Just as you iterate the O-sharp mouse and it generates the indiscernibles for L. And what I can think of this LE0 is it's somehow the minimal inner model for a proper class of measures. I mean, of course, I can iterate the measures in this model and get different models for the proper class of measures, but somehow in one sense, this is the minimal one here. So this model, LE0, it started off from this countable mouse, M0. So a lot of its measures are countable, right? In fact, it's going to have below the V omega 1, it's going to have omega 1 many measurable cardinals, and ditto beneath other cardinals. So what we do now is iterate this model LE0 to line up its measurable cardinals with the closed unbounded class that we're interested in. So let's take C as the class of cardinals. And we're going to define a proper class function, this little c here. And the alpha function here is just going to be the sequence of the omega many measurable, the omega many alephs between aleph omega alpha plus 1 and aleph omega alpha plus omega. And the sup of the C alpha is going to be this mu alpha. So this is just this simple limit of alephs. Right? So it's the alpha simple aleph limit, something of the form lambda plus omega here. And the idea is that these C alphas, we're going to arrange this so that this is going to be prickly generic for a measure defined by this final segment filter on the C alphas in this model LVC that we're generating in this way. That's the picture to kind of grasp here. Well, we're not going to do this just for card. And I said card over here for C. We're going to do this more generally for appropriate classes. So a class is appropriate if it's a CUB subclass of these generating indiscernibles for OK. Right? So again, remember, these are closed unbounded beneath each uncountable cardinal. OK, so we've got some class, which is a CUB subclass of this that we're interested in, which we're calling it as P. So just as P might be the alephs, let lambda iota be the enumeration of P here. So now just let CP alpha just again be enumeration of the successor elements of P here. And we'll let mu alpha again just be the simple limits of these elements of P. And again, we're going to think of a model LEP here, right, which is going to hopefully have a sequence of measurable cardinals, mu alphas, where the measures are generated by the C alphas. Now, unfortunately, I've got some rather full slides here, but I'll just try and point out what's the relevant stuff here. So for convenience sake, let's consider a fixed point in the enumeration of these indiscernibles. Just some large cardinal, if you like. I mean, high up cardinal, right? So we'll define a forcing, which is going to be a direct product, full direct product forcing of prickly forcings below nu here. And some notation just here is a sequence of measures of length nu here. And I'm going to have these product prickly conditions. And I'm going to have two components here. There's going to be a sequence of measure 1 sets given in this direct product. So a new sequence of measure 1 sets from the various U alphas. There is going to be a function giving me the stems in the forcing here. But only finitely many of these stems will be non-zero. So actually almost everywhere, this pair HH, the little h is going to be just empty, the empty function here. There are various other things that tell us that something, the components, little h alpha and big H alpha is a precondition. And extensions of these functions would just be done coordinate-wise. Okay? So if f extends HH just means that every coordinate, f of alpha extends h of alpha. Right? And f of alpha, the difference between f of alpha and h of alpha, this will always be there inside h of alpha here. But again, the support of f is finite. So there's actually only finitely many alphas where there's a difference. Okay, so this is the full Easton product of, sorry, the full direct product of these forcings, right, up to p nu, giving us p nu. So if I've got a generic over this model for this forcing here, we can define, as one would do usually, the sequence of Pricry sequences to be just the union of the stems, right, for which we've got conditions, right, these long conditions going up to nu in the generic here. So now I accidentally went to the next slide. If you look at what P nu is, it's something, it's got the nu plus chain condition because it's this full product that's going on here. So Gunter Fox gave a nice characterization of when you've got generics in this sense over such models, right, here. And this was to mirror the Mathias condition for forcing just on a single measurable. So, and it's beautifully succinct. What one has to do is you take any new long sequence of measure one sets here, and then you look and see where the stems miss this long sequence. And actually, it can only not be fully contained in the alphath coordinate at finitely many places. And at each of those finitely many coordinates, it can only miss any measure one set at finitely many places. So it's quite a stringent condition, if you like. It has to take any, to repeat, it has to take any measure one, any sequence of measure one sets, and has to lie almost entirely in all of them. And there are only finitely many places where that can go wrong. Now, this condition works in this scenario here because in the model LEP that we're talking about, we don't have any measurable limits of measurables, right? This was the necessary condition for his analysis. Recall that what we did was we only put measures on simple limits of the cardinals. The Alephs of the form Aleph lambda plus omega, or simple limits of our appropriate class P that we're interested in. So all the measures were discrete. They didn't interfere with each other. And that's what's going to have to change if we wanted to talk about something like LReg. Right? Yeah. So let me bring out for later this property, this kind of Fuchs's property here for just in general. I've got a set of measurable cardinals delta. And again, I've got a sequence here, C alpha, for each of these measurable cardinals. And I'm going to say if I've got my normal measure U alpha, the sequence C vector has got the U vector set property. Again, if I take anything out of this product, and now they're A alphas rather than H alphas, I guess. And if they're all of measure one, then the sequence C vector hits the whole of the direct product of the A alphas almost everywhere. So this will be called the U vector set property. And this will come back later here. But before we go on, I would just like to point out, right, something which that shouldn't be there, that should be here, right? Because of this very stringent genericity property, it's very, if I just finitely tweak a generic, by the Fuchs condition, I won't have destroyed its genericity. So actually, I could take a P new generic. I could take any condition at all. And it's easy to find a sequence which is still P new generic, right? Which is only finitely different. Right? It's symmetric difference everywhere from the original sequence is just finite. But now I've got P in GD, right? All I have to do, right, is, well, it's a prescription in this bullet point down here, right? But you can tell what's going to happen. All I have to do is just change the elements of C alpha so that it's got the stems of P alpha, the various P alphas in it. There are only finitely many stems P alpha that are non-empty anyway. So I don't have to do much. And then I take that P, and with the rest of the things that I get from my generic GC, I could just get my GD. So it's easy to just change this C so that it accommodates any condition at all. But this is going to give us some kind of weak homogeneity, right? If I've got a formula here, right, and I've just got some ground model names for this should be elements of P, I think here, not EP. So this is a mistake, right? So think of these as ordinals in P. If something is forced, actually just the top condition forces it here, right? Because any condition does by the corollary above. So the top condition does. So that's going to be behind the idea that we can get the theory of the generic extension is just going to be the same, right? It's just going to be given to us as an element. It's just a set in our ground model, that theory. So that was talking about I don't know if there are any questions you want to ask at the moment. That was just talking about the product up to some largish cardinal nu, right here. We want to do this throughout the class, appropriate class P, or the class of all cardinals. And so we did want to stretch this idea. We want to just take the forcing P, this direct, full direct product up to nu, and take it up to infinity, take it up to ON throughout the top of the universe here. So there are just one or two little things that we have to kind of think about and take care of here. If I've got something that's generic over LEC, because we had here the nu plus chain condition, it's equivalent to saying it's just P nu generic over, well, it meets all the anti-chains that are there, actually in H nu plus of LEC here. So what we have to do is we look at the external mouse that generated these points like nu here, and we stretch this H nu here to be this direct limit model through the ordinals of all of these H nu plus models. Now there's some scare quotes around here because this direct limit model, of course, this goes beyond the end of the ordinals. And so I've written down here ON plus or something down here to indicate something like this. So really, this H infinity is the direct limit of all of these H iotas, of these H nus. And the point is that this forcing now has, it doesn't have the ON chain condition. It has what you might call the ON plus chain condition in this model H infinity here. And it's natural to think of this as being something like a Kelly-Morse model, right? Or if you like, we're talking about generics over models, which are kind of hyperclass generic here. So that's one thing that we kind of just have to think about a bit here. But it's the definability of the forcing P nu over this model, together with the fact that we're going to stretch this model here up to this whole class model here. You know, this nu here was an indiscernible, right? These L nu EPs, these are elementary in the full model here. So the weak homogeneity of this P infinity forcing is, this is what's going to yield the definability of the theory of LEP with this class generic. So we're now going to have a proper class generic, this full direct product. The conditions themselves will be proper classes in this forcing. Again, only finitely many non-empty stems, but a proper class of measure one sets here. And we'll get the definability of the theory of the extension is just definable over any one of these models because of this elementarity. And this is the elementarity that we're going to get between the different LEP models. Right? So to summarize, if I've got this O-cookery and I've got P in appropriate class, I can think of this LEP, right, which we generate by taking this iteration of the least inner model with the proper class of measures. And this will be the kind of the K. This will be the core model of LP. In this LEP, we made sure that the measurables were just these simple limits in the enumeration of P here. And the enumeration of the successor elements of P, which we partitioned off into these C alphas, these were the individually, but also full product prickly generic forcing, according to the Fuchs condition that we had there. So what we end up with is that L of this class is just the same, it's literally just L of CP here, together with its other limit points, but it's also this generic over its core model here. So to state a little bit more that we get from that, we now know that a lot of properties are true in LP. Right? Actually, any simple limit Aleph is, well, it's the limit of a prickly sequence. It's Johnson, it's a Johnson cardinal in LP. These C alphas are these prickly points. These are all Ramsey cardinals there in the model. But in LP, there are no measurable cardinals. They've all been singularized. But it's got lots of nice properties. It's certainly a model of GCH, but it also has things like diamond squares, combinatorial principles that it inherits, just simply by virtue of being a nice generic extension of a core model with these properties. There's a nice delta 1,3 well order of the reals, and we know exactly how much determinacy we have inside this model here. So there's a lot to say about such models. Okay, so now we want to go to LReg. Unless there are any questions that you want to hold me on that point. Okay. So now the difficulty is that we're going to have to consider measurable limits of measurables. Right? Because we may have regulars, we may have inaccessibles, which of course are going to be limits of successors. there may be regular limits, sorry, inaccessible limits of inaccessibles and inaccessible limits of those, and so on. So we've got a whole kind of mess of inaccessibility that we have to deal with. And we're going to see how we can do that here with this, using now a larger mouse rather than OK, but still pretty small beer actually when it comes to mice. It's just the least mouse whose top measure now concentrates on a set of measure 1 of measures below. OK just had measurables unbounded in its top measure. This one has a measure 1. It's got 2 measures at the top, an order 0 measure and an order 1 measure. And this is the first mouse with 2 measures on the same measurable cardinal here. So we're going to do the same kind of thing before. Let's just consider reg now here. So let's fix this class of regular cardinals. Now, of course, to make matters interesting, let's assume that there are lots of inaccessible cardinals around. Right? Otherwise, LReg could just be the same as LCard if there are no inaccessibles. So we're going to assume there are lots of inaccessibles around, and we're going to assume that this mouse O sword exists and try and develop the same picture. So it'll start out in the same way. Right? I can take this iteration of O sword here, and I'll take the least measurable cardinal. It's got a countable, it's a countable object again. It's got plenty of measures up to its top measurable cardinal. We'll take the least and we'll do what we did before. We'll align it up onto Aleph Omega. So that's the least simple limit of regulars. So when we've done that, we've got a structure sitting on Aleph Omega. So let's take the least measurable that it's got above, strictly above Aleph Omega, and we'll align that and put that onto Aleph Omega plus Omega. Right, so we've got 2 measurable, the bottom 2 measurables lined up on the first 2 simple limits of regulars. So we keep doing this, right? The picture is just, we keep doing this. But there are going to be points where we're now going to get, for example, regular limits of regulars, right? We're going to have to use not only just the fact that there are measurable limits of measures in this mouse OS and its iterates, but we're going to have to use the fact that there is this measure 1 limit of measures, right? So if V has got, even unboundedly many, let's say, inaccessible limits of inaccessibles here, there are going to be inaccessible stages where in the model of the lambda stage here, lambda is going to be the image of critical points from below arising from this alignment process. So the small object from the point of view of lambda, it's iterated up to lambda. And what we'd like to do is, well, we'll take the next measurable cardinal, if it's got one, and use that to go to the next simple limit. Or if this lambda's inaccessible, we don't want to, sorry, I misspoke there. I don't want to leave measures on inaccessibles. I only want to end up with measures on simple limits of regulars. So when I iterate up to this inaccessible, I'm going to iterate some measure up to this inaccessible point. So I want to get rid of that. So I'll iterate that up to the next limit, simple limit of regulars here. And then we continue then again in this fashion. But we're going to have to leave measures behind at some point. So we need a mechanism for adjudicating when this happens. So what we'll do is we'll just look at now perhaps a singular lambda, and it's going to be a cofinality omega. So this is kind of the interesting case here. I've got a lambda of cofinality omega, and it's the sup of previous images of inaccessibles. So actually, it's the sup of an omega sequence of inaccessibles where we took a critical point and we iterated it, and it ended up at the next row k plus 1. And this happened for all the k's less than omega. So we ended up with the image of these rho lambda k's right here being this rho lambda omega at this stage. So if lambda's of this form, right, okay, it looks good, right? It's a simple limit of inaccessibles. So we'll leave a measure there if we can. So we'll look and see whether there's a least measurable in the structure we've got to this stage above lambda and use it to go to the next simple limit Aleph, right? So if we can, then yes, then we do that. So we'll leave behind then this measure on lambda in this case. And this is the image of the measure that came up from the row case here. So otherwise, right, if lambda's a singular cardinal in case 3 isn't happening, right? Perhaps if this is a singular cardinal of some other cofinality, it's perhaps not a simple limit Aleph, right? We would take the next unused measure, which iterates up to the next simple limit. Now that next unused measure, right, here, shouldn't be, right, the order 1 measure, right? We're just going to be leaving here, right, the order 1. We use the order 1 measures to leave behind measures on the simple limits of the regulars here. So anyway, once one has absorbed this, the upshot is that you've got a model here where the measurables are now the simple limits of the Alephs or the simple limits of the inaccessibles here. So that's what our LER is. Well, that's the model, but not quite every inaccessible has been accounted for as one of these row alphas here. There might be finitely many of the inaccessibles that we've actually missed out. And it might look a bit peculiar at first, but actually, if you think about it, take the kind of trivial case. Let's suppose there are only finitely many inaccessibles in V anyway. Right? Then actually our construction process actually won't pick these up. It'll just take some least measurable cardinal and put these on the simple Alephs, limits of Alephs, but there are only finitely many inaccessibles, so there's no omega limit of inaccessibles for it to leave a measure on. So actually then these row alpha ends will become like orphans, right? They won't have been taken care of, right? And they'll just disappear from our analysis. But there's only finitely many of them. If there were an omega sequence of them, then there'd be a measure corresponding to it. So that idea means that we could have missed finitely many inaccessibles. But actually, there's another reason perhaps for missing inaccessibles. It's just that perhaps we've got finitely many inaccessible limits of inaccessibles, and also only finitely many, and above those, only finitely many inaccessibles. And then we kind of be leaving behind the finitely many inaccessible limits of inaccessibles, and then we'd be dropping down to kind of an initial segment of the mouse to kind of do the rest of the iteration through the ordinals. So we can leave these finite sequences of orphans behind, because we have to kind of cut down in the mouse ordering that we're using, is perhaps the maxim here. But because the mouse ordering is well founded, we're only going to be doing this cutting down finitely often, and each time leave behind finitely many inaccessibles. So, I mean, you don't have to worry if that made little sense to you, but we need that lemma. And a recent result of Oma Benaria gives us a kind of generalization of Gunter Fox's criterion for a Mathias-like condition for the, now it's going to be Magidor iterations rather than full direct product of prick reforcings. It's going to be Magidor iterations of prick reforcing. And the key property here, besides the U vector set property of Gunter Fox, is this strict separation property that our sequences here should enjoy. So just in general, if I've got a collection of omega sequences, and let's say again, C alpha is a subset of alpha, just abstractly, I'll say that C vector is the strict separation property if there's no kind of interleaving, right? I may have some nu and some kappa here, where nu is in C kappa, but I don't get any interleaving with for some larger C kappa prime of a nu prime. So nu prime isn't going to fall down below kappa if kappa prime is bigger than kappa. I only have the prickly point with the measurable strictly kind of divorced from prickly points and measurables of larger measurables here. So what we have then is this theorem of Benaria, right? So again, assume that we're doing this for, he does this for sets of measurables. Let's suppose we've got a sequence of things that look like prickly sequences for separate measurables. Suppose here are the measures that we're concerned about, and we have the Fuchs separation property for these, for C vector, these C alphas here, right here. But if we have both the set, sorry, if we have the Fuchs U alpha set property and also the set separation property that I've just mentioned on the previous slide, if we have these two conditions together, this is enough, Benaria shows, to get Magidor genericity over the sequence of measures, even though there are clusters of measures, measurable limits of measures, measurable limits of those, and so on. So the Benaria argument here, this works when you have order zero measures. But in our construction, those are all order zero measures that we've left behind on those points here. And the construction will ensure the separation property, this de-interlocking here, if you look at it. And you can think of the forcing here as just taking place over, an old style Kuhnen in a model just constructed from the sequence of measures here. You don't have to think of this as coming from L in a model which is constructed from a filter sequence in the way that modern fine structure is also done here. Okay. So what one gets from this, right here, is that OSORD is not in LReg. We used OSORD to generate the core model of LReg. So OSORD remains outside LReg. LReg is just the generic extension of this model that OSORD has left behind. Right? On the other hand, let's suppose OSORD exists. what we did in that construction, right, is took a mouse and iterated it. And I kind of alluded to the fact that actually there may be some cut downs or proper initial segments of iterates of this mouse. That's all that's needed to do this construction, because we may be short of inaccessible cardinals in V. Inaccessible cardinals in V may just be inaccessible limits of inaccessibles, nothing more complex. In which case we won't need all of OSORD in order to construct the model which is going to be the core of LReg. Something less would do. So the question then arises is, did we use the least mouse? Did we use the least iterable structure in order to do this construction? And the answer is yes. Right? It's consistent that the structure of the regulars, the inaccessibles, is such that you couldn't have done this with any smaller mouse. Right? And that's a special case of this final statement down here, right? Which just says, I could have started this construction process using any subclass of the regulars at all. You could give me any subclass of the regulars, and we could have done this process, found a generic class over the model that's constructed. But this construction wouldn't have brought OSORD inside that model here. Right? So OSORD then, as claimed in this bottom part here, is going to be the minimal possible mouse for which one can do these kinds of constructions in general. Right? And so that argument shows, if the ordinals are Marlow, then OS, if it exists, this is the star least mouse that's not in LReg, right? And so no smaller mouse is going to actually cope to do this kind of iteration here. Okay, any questions at this point? Okay, I'll just finish perhaps then going through I was allotted 60 minutes, but I did start a little late. Let me just perhaps just show you a little bit about what I was talking about, these generalized L universes constructed using stronger logics. So again, you could just take this impressionistically. So this is taken from this paper at the bottom here. So the Hertig quantifier it looks kind of somewhat artificial at first place. So it's a quantifier over two formulae and variables X and Y. And this quantified construction, the syntactic string, right, is reckoned to be true in a model if, when you look at the collection of objects that phi defines, it's got the same cardinality as the collection of objects that psi defines. So this is information from V, right? So this is being fed into the construction of this L-like hierarchy. So we start from the empty set, as in for L, and now we look at what's definable over a level, but using this stronger logic, the stronger quantified language. So we're not just taking what's definable in the ordinary first order sense. We allow ourselves to feed in information from V about certain sets that we are currently defining or already have defined. Right? So we end up with a model here, right, which has got all sorts of extra information in from V, which is imported as information. So actually, if you think about it, there's no reason when you define L of I inside L of I, you get back L of I again, right? It needn't be absolute. Rather like constructing HOD inside HOD, this needn't be HOD. Right? So they call this model CI. So going back to the first part of our talk, when P was card, this model CI is not too hard to see. It's just L of card, right? Just for the predicate of the cardinals, right? So in this model, it's perhaps more perspicuous. In the model, there's an alarm bell that goes off, right? It tells us which ordinals V thinks are cardinals, but it doesn't tell us anything else, right? So the model knows which things it thinks V are cardinals, but it doesn't mean it adds any more functions. Right? So it turns out what we can say is that if this mouse OK doesn't exist, then K constructed inside this model is the true K, right? Now, I don't mean here the model L card constructed as before, because that assumed OK for its construction. Here we're talking about models that could be gotten from anywhere, right? Forcing extensions of L, who knows what. But if OK does not exist in the universe, this CI always has the true K inside it. In particular, as a rather weak corollary here is, if V is an L of E model, but it's a small one, it doesn't have OK in it, then V equals CI in this sense, like V equals HOD. So we can do this for our regularity quantifier here. So define here R of X holds this formula, and now it just feeds in the information about whether this set has got regular cardinality or not. So the same format, we get the same model using this logic, same construction of a model using this logic. But now we're feeding in more information, not just what are successor cardinals, and of course, what are limit cardinals we get as limits of those inside L of R, but also it tells us which ones are regular, right? It doesn't give the singularizing functions inside the model L of R. It might be that aleph omega is again it might be a regular cardinal in L of R, right? But we get exactly the same kind of results about the core models here, right? So CR is just LReg. It's not hard to see here. And again, if the universe is not too big, wherever CR comes from, right, its K just is the true K, the true core model of the universe, V here. And again, the same thing happens if we're inside an L of E model, right? Then V is just this model here. And of course, then CR constructed inside C of R is just C of R, right? Here. So we can get probably the more interesting point here is this second thing here, is that we can, if the universe is not too big, no matter how we've constructed this C of R model or this L card model, its universe, its core model is the true core model of V here. Okay, fine. That's all I have to say here. So thanks very much for that extended talk.
Thank you very much, Philip. That was really, really interesting. Questions for Philip, if any?
What are those objects?
This is a minimalist piece of art by Carl Andre.
Oh, right.
It comes from the, I can't remember her name now for a moment, it's escaped me, the Guggenheim Villa in Venice.
Oh, yes, yes. Yes.
We started off with minimalism with Yves Klein, and we ended with it, right? And it was minimalist throughout the talk, I'd say, because we were just talking about rather small mice all the time.
Right. Well, Peggy Guggenheim, was she?
Yes.
I think that's right.
That's right.
Yes. Ah,
Are there still any interesting questions left in this area?
Well, yes, I think so. I mean, there's a whole lot of, I mean, it becomes perhaps more finely grained, right? You could look at just the reg 0 predicate, which might be just inaccessibles, which are not limits of inaccessibles. And then you could look at the reg 1 predicate, which consists of reg 0 inaccessibles plus inaccessible limits of those. So you go through the hyper inaccessible hierarchy here. And corresponding to that hierarchy, there should be a hierarchy of mice which are actually generating these core models here. Right? And one can ask then, you know, what kind of, we're using the Berneria kind of and Magidor iteration results here, but we're saying that the measurable limits of hierarchy doesn't get too complicated. So there's probably a stratification of all your regulars predicates as you go through. I think it's called, is it hyper inaccessibles, which are inaccessible limits of inaccessibles and so on. And one can answer questions like that. Yeah. If you move off the regular cardinal hierarchy, I think the most interesting question left is, well, there are quite a few questions, but the next interesting question is the co-Omega quantifier, where this quantifier brings in from V the information as to which ordinals have got cofinality omega. So in particular, it'll tell you that this particular point is, which is aleph omega in V, is actually, it tells the model this is a singular point. Right? So the question then is, what is L cof omega? So I just take the predicate for the cof omega ordinals, and what is L cof omega? How big is that? Right? And there's some kind of discussion. Well, some people think that L cof omega is a rather fat model, and it may have lots of mice in it, in models with lots of large cardinals in. And I myself am kind of betting that the L cof omega is rather thin. It's rather hard to show that there are stronger mice inside L cof omega. You can show that O sword is inside L cof omega. Sorry, you can show that things stronger than we've got here. Sorry, what have I got? No, you can get O sword inside L cof omega, right? But it's hard to get much more. Right? I don't see reasons why L cof omega should be much bigger. Everything that people have used large cardinals on, Wood-in cardinals, proper classes of Wood-in cardinals, they've used to get absoluteness results to say things about the cof omega model. None of those are inconsistent with the cof omega model being very small, actually very thin. So though heavy machinery, heavy artillery is being brought to bear on studying L cof omega, there's still no proof yet that it's got inner models with very large cardinals in. So that, I think, is a very interesting question that's left.
How do you see that O sword is in it? Is it difficult?
I'm not, I'm just wondering whether I said the right thing there. I might have to look at my notes at this point. Sorry, I misspoke there. We know that O sword is not in LReg 0 and LReg 1 and LReg 2 and things like that, right?
Right.
We don't know that O sword is not in LReg. Sorry, we know that it's not in LReg. We don't know that O sword is not in L Cof omega.
So we don't know. Okay.
We don't know that, right? I think that's the right
Okay.
thing. That I feel confident to say that.
So basically nothing is known, really.
Oh, yes, good idea.
Sorry, was that a comment, Adrian, or a
Sorry, no, my supper's almost ready, and I must
Right.
thank you. I learned a lot from your talk, Philip. Thank you very much.
Right. I hope your supper is fine. Right. Okay then.
Yes.
Goodbye to Adrian then. Right.
Goodbye.
Okay.
How do I exit?
Well, you mute first, and then you can exit.
Anyone else have questions?
All right.
I have a question.
Sure.
In the first part of your talk, there was this attractive property about these models constructed from club predicates, that they all turn out to be the
Yes.
L equivalent and so on. Do you get similar results for L of reg and predicates that are somehow equivalent to maybe mod non-stationary, the same as reg?
Right. I mean, I didn't think about this very hard. All I thought about was just this idea of just taking any subclass of reg, and this was just these results here, this bottom one down here, right? If you start trying to think of anything different, because reg is not a closed class, of course, you end up saying things like, well, take another class of regular cardinals, and let's suppose it's got the same order type as reg, and where it's got limit points, it had better be that the order type beneath those limit points is the same, right? Because they're regulars. So any regular lambda's got to have lambda regulars, successors beneath it. And you end up saying things so that ending up putting conditions on it, so the classes then don't become too interesting. I mean, they can be different and still have the same elementarity. I could think of another class S, which is not much different from reg, but it better have the same limit points as reg, but it needn't have the same successor points in it. And then you would get elementarity, but if you then think about what you're doing, actually it's not terribly interesting, right? It's not as nice as the CUB classes that you got for L card and the appropriate P there. Maybe there's some more to be said here, but nothing terribly nice came up.
Thank you.
You're welcome.
Anyone else? All right, then let me turn off the recording first. All right, Philip, thanks again for the great